to all. My name is Ganesh Bhandari, and I am a PMRF PhD research scholar in IIT Roorkee. And I am here for the live session, week 11 for the NPTEL course, Principles of Extractive Metallurgy, taught by Professor Tarun Kumar Kundu from IIT Kharagpur. We will start, as usual, we will start with the revision of the previous week lectures. Then, based on the previous week lectures, we will try to solve some MCQ type problems, which will ultimately help you in solving the assignment problems based on the uh, lectures. So first we will go with the revision of the previous week lectures. Before this week lectures, we have learned about various refining processes and extractive metallurgy processes of various metals like tin, copper, iron, what type of furnaces are used for those extractive metallurgy, those pyrometallurgical processes. However, the main thing is this, during the pyrometallurgical processing of any ore or any metal, we can get a purity of particular metal up to a certain level. Like if we talk about the copper metal, during the pyrometallurgical operations, we can get a purity level of around 99% or so in case of copper. However, if we are trying to make the wires with the help of this that copper metal produce, we need much higher purity than 99%. We for making wires to be used in the for current flowing, we need a purity of at least around 99.9% or sometimes maybe more. While if we talk about the semiconductor devices, then we are going to need much more higher purities. Like if we talk about silicon in semiconductor devices, then we need a purity of around 99.9999% there. And that can be done with the help of only Siemens process. So, however, that Siemens process require at least metallurgical grade silicon, which can be produced with the help of pyrometallurgical operations. With the help of pyrometallurgical operation, we can get a purity of up to 92 to 93%. But to reach a level of 99 point triple, at least 59 purity, we have to go with the Siemens process. So these types of processes are generally considered as the refining processes. There can be physical refining processes or chemical refining processes for the refining of these crude metal, which has been produced with the help of the various pyrometallurgical or hydrometallurgical operations. So, in this week lectures, first we will talk about the chemical refining processes of zinc, tin, nickel, and titanium. And along with titanium, we will also talk about the zirconium, hafnium, and thorium chemical refining processes. So, generally, when we produce the zinc with the help of the pyrometallurgical operations via generally it is done with the help of the imperial smelting process. By whatever the zinc we are going to produce with the pyrometallurgical operation with the help of that imperial smelting process is of lower grade, and then that produced by the hydrometallurgical methods. So refining is necessary to achieve a desired grade which for zinc metal which can be reused back in further applications. So we can achieve this refining via two different processes in case of zinc refining. First one is precipitation of the impurities from the melt to yield 99.5% zinc purity, or we can go with the fractional distillation process to yield 99.99% purity zinc material. So based on the requirement of the purity, we can choose our process, like we can go with the precipitation process via melting, and then or we can go with the fractional distillation process. As suggested, we need to go with the, in both cases, we need to go with the pyrometallurgical operations for the refining. However, the temperature can be working temperature can be different in both processes. So coming to the precipitation method process. So in the precipitation method, crude zinc, which can have a purity of around 96 to 97% sometimes, uh, it is to be melted in the reverbatory furnace, having around 150 tons capacity. And the molten bath is held at a constant temperature of around 420 to 450 degrees Celsius. Zinc melting temperature is around something like 400 or something temperature, then we have to maintain this molten bath at a temperature of around 420 to 450 degrees Celsius for at least 24 to 48 hours. So what will happen during this melting process? Some materials present inside this zinc bath will get melt according to their melting temperature, and some will not get melt down. So they will still be in the uh, molten. Some will be in the molten metal state, or some will be in the solid state as of now. So when we are going to hold it at for around 24 to 48 hours, so what will happen? The metals present inside this zinc bath will get separate according to their density. Okay, so what will happen? The material which is having lower density, that will come on the top, and the material which is having higher density will go down in the bath. Or the metal which has not been melted yet at this particular temperature will go down in the bath. So it will separate into three different layers. First one is top layer. So it will contains zinc purity, zinc which is having purity of around 99.5%, and some impurity in the form of the lead. Around 0.5% lead will be there. So that will be separate out in the top layer. While in the middle layer will contain the iron impurities as an iron zinc alloy and Zn7 dross, which is stable up to a temperature of around 647 degrees Celsius. So, as of now, we are holding it at around temperature of around 420 to 450 degrees Celsius. So, it is not going to get melt. So, it will form the dross, and it will separate out in the middle layer. While in the bottom layer, we will found some lead impurities and a small amount of the zinc impurities, around 4 to 6% zinc is going to loss during this process. So a part of the top zinc layer, about one third of the batch, is drawn out of the furnace at regular intervals, and fresh crude zinc is added. The dross and the layered layer are removed periodically as they accumulate. So that process is this process which we are going for the refining is going continuously. We are continuously removing the top layer of zinc layer from the top layer, having 99.5% zinc, while we are also removing continuously the middle layer and bottom layer in the form of dross or slag material. Then coming to the fractional distillation. So in the fractional distillation process, we generally go with the imperial smelting type process, and we do it at a temperature of around 1100 to 1200 degrees Celsius. So zinc gets evaporated at that particular temperature, and then we are going to condense it so that we can get the pure zinc material. While other materials are not going to get evaporated at that particular temperature, so they will remain as impurities in the uh, material in the molten bath. Then precipitation of impurities like tin refining. The refining of tin is complicated because it involves numerous operations. Like all the processes are conducted in the same kettle, and it takes about 40 hours to complete a batch with a yield of around 87 to 88% of the raw tin. First, in this tin refining operation, we go step by step. So in the first step, we consider the removal of the iron. So Fe from crude tin is removed in two steps. First one is dross formation. So on cooling, crystals of FeSN2 separate out on the surface and are removed with the skimmer. So first we are going to melt down this tin material, and on the cooling, we are going to get the crystals of FeSN2 material, which is going to get separate on the surface and can be removed with the skimmers. The dross obtained is returned to the reduction furnace to recover tin, and iron enters the slag. So this dross we are again recirculating back into the reduction furnace, which we have talked during the pyrometallurgical operation of the tin pyrometallurgy. Then the remaining residual iron is removed as a matte by adding some sulfur. So, sulfur is having high affinity towards the iron as compared to the tin material. So, sulfur, when we are going to introduce the sulfur inside this melt, so it is going to get react with the iron, and while making iron sulfide material as a matte. So, we are going to get it. So, it is going to get separated in the slag formation. Then in the second step, we are going to remove the arsenic and antimony material. This is achieved by adding aluminium to the molten tin. After removing the iron from the tin molten bath, we are going to add some aluminium inside this molten tin at about 550 degrees Celsius. And this tin is going to get reacted with this arsenic and antimony present inside the molten bath and going to form the dross material and like AlAs and aluminium antimony, aluminium arsenic, and aluminium bismuth, aluminium antimony compounds, which is having very high melting temperature of around 720 degrees Celsius and 1000 degrees Celsius respectively. So we are maintaining the bath at around 550 degrees Celsius. So it is going to get up on the surface due to their high melting points, and we can easily skim out this material from the molten bath. Then after this, in the third step, we are going to remove the bismuth material, and this can be achieved by adding calcium and magnesium at a temperature of around 380 degrees Celsius to form a dross composed of Bi2Mg5, Bi2Ca3, and Bi3Ca, and these all dross compound are ceramic in having ceramic nature, so going to have a very high melting point and going up, uh, going to report upward in the upward layer, and we can skim it off for removal of the bismuth material from tin. So after this, we can get a high purity tin material. However, in this whole process, we are going to lost around 12 to 13% of the tin material. However, that tin can be again recovered back with the help of the reduction furnace. Then coming to the refining by chemical transport method. So refining by chemical transport involves the formation of a volatile compounds of the metal to be refined by means of a reactive gas, followed by its decomposition to yield the pure metal and to regenerate the reactive gas. The metal is thus transported from the impure solid form as a gas and then redeposited in another vessel. So it is like we are going to decompose the material with the help of the some gaseous compound. We are going to react the material with some gaseous compound, and they are going into the gas form, and after they are going to in the gas form as a volatile compound, and in the again in the second furnace or second reactor we are again going to get them decomposed to recover the pure metal and the gaseous gas material which we have provided for making the compound. So this type of chemical refining processes involve three different processes. Like commercial process is carbonyl process, known as Mond process for refining of nickel material, while iodide process, which is developed by Van Arkel and D. Bohr, for the refining of titanium, zirconium, hafnium, and thorium metals, and the pilot scale subhalide process, which are generally used for the refining of metal by chemical transport. So coming to the carbonyl process, so certain metals like middle position react with the carbon monoxide to form volatile carbonyl compounds. Like metal is going to get reacted with the carbon oxide to create metal carbonyl, which is having a evaporation point of which can have a evaporation point of sometimes around 1100 or 1200 degrees Celsius. These carbonyls can be collected and decomposed by heating to form the metal and regenerate CO for recycling. So first we are going to get them convert. First we are going to convert these particular metals, like for example nickel. We are going to convert them into the carbonyls enough, so we can collect them in the gaseous form, and then we are again going to decompose this gas to collect back our metal and the reactive gases so that we can recirculate back this reactive gas. These carbonyls can be collected and decomposed by heating to form the metal and regenerate reductive gases for the recycling. The temperature at which the carbonyls are formed and decomposed vary widely. The reaction rates at which CO reacts with different metals vary, thus it is possible to achieve selectivity for the metal to be refined. So, like temperature for the formation of carbonyls vary according to the different metals, and this is having very wide range. So we can operate selectively which metal to be get converted into the carbonyls, and then decomposition, via decomposition we can recover the pure metal. A mixture of carbonyls may be separated into its component by fractional distillation, like for example, NiCO4 is a colorless liquid at room temperature and boils at around 43 degrees Celsius, while FeCO5 has a boiling point of around 103 degrees Celsius only. So, just boiling at around 50 degree or 100 degrees Celsius, we can recover our particular metal with the decomposition process. Then, coming to the carbonyl process, which is generally used in the nickel refining, which is also known as Mond process. So, nickel carbonyl was the first metal carbonyl discovered by Ludwig Mond. So we have named this process on as Mond process in England in 1819, and the refining process based on its utilization is known as the Mond process. Finally divided nickel powder reacts in rotary kiln or catalyzed by sulfur or hydrogen sulfide gas with dry CO at around 80 degrees Celsius, and most of the Ni and only a small fraction of Fe will volatilize as carbonyl impurities, and carbonyl, while impurities will remain as a solid residues. So, then we are going to capture this nickel carbonyl, and with the help of the decomposition of this nickel carbonyl, we can uh, get back the nickel metal with high purity, while CO gas recovered during this decomposition process can be reused back for the uh, for making the metal carbonyl again. Then we can play with the temperature during this nickel carbonyl refining process. With the help of the temperature increment, we can decrease that. With the help of the pressure increment, we can decrease the temperature or increase the temperature during during the refining process. Then coming to the another method by chemical transport, which is known as iodide process, which is also considered in the halide metallurgy. Which is a part of halide metallurgy. So the refining of metals by thermal decomposition of their iodides is known as the Van Arkel and de Boer process. It is essentially purification by chemical vapor deposition and extensively used to ultra refine rare or refractory metals. So a volatile iodide, which is having which are least stable halides, is formed by the action of iodine with impure metals, like metal crude getting reacted with iodine gas, and it is going to get converted into the metal iodide, which is also in the gaseous form. And then we are going to decompose this metal iodide gas in a different chamber to regain the pure metal and the iodide gas, which can be reused back for making the metal iodide. So, metal iodide, which is having a gaseous formation, is subsequently decomposed at a temperature of around 1200 or 1300 degrees Celsius to deposit the pure metal and liberate the iodine for further reactions. Here, iodine act as a transporting agent. So, this in the previous process, the CO gas was acting as a transporting agent for the metal to get them converted into the metal carbonyl, and to get them separated in the gaseous form so that we can decompose this gaseous form in the another reactor. So this type of process is known, that's why these processes are known as refining by chemical transportation method. So here iodine act as a transporting agent. According to the Leach-Atelier's principle, iodide formation is favored at higher pressure, whereas the decomposition is favored at reduced pressure. So highly reduced pressure will restrict the throughput of the metal, and 10 to the power minus 3 to 10 to the power minus 4 atm pressure is generally used in industrial practice. So many metals form iodide. However, the process is limited only to metals having high valency, such as titanium, zirconium, hafnium, and thorium. On the other hand, we can say that this process is restrictable to these metals only, because these metals are considered as strategic material and having higher cost add up in the economic of the process. If we are talking about if we are going for the for example, if we are going for the refining of nickel or iron via this iodide process. So what will happen? We are not going to have the economy of, we will not be able to we will not be able to uh, handle the economy of the process. The process will become much uh, uh, much costlier, while we will not get the same price for the product obtained during this refining process. So we generally consider various factors. So we generally use this process for the refining of metals which is having high valency and very high strategic cost. So we generally go for the refining of titanium, zirconium, hafnium, and thorium with the help of this iodide process. So due to the high positive charge on the ions of these metals, their small size as compared to the iodide ion, iodides of these metals show great instability. Other iodides will evaporate but not decompose at these particular temperatures, so it will be difficult to uh, extract back the metals from from the metal iodide. So that's why we generally do not go for the metal iodide refining processes for most of the metals. Then refining by chemical transport. A single reactor is used batch-wise for the formation and decomposition of the metal iodide. The metal, including titanium, zirconium, hafnium, and thorium, to be refined is charged in the annular space between the walls of the reactor and a perforated molybdenum tube situated inside the reactor. A side arm of the reactor contains the iodine, while the decomposition filaments, having 2 to 3 millimeter diameter, made of the same metal to be refined, or tungsten we can keep, is kept in the middle of the reactor. The apparatus is then heated in a furnace at around 400 degrees Celsius and the electric current is passed in the filament so that the temperature of the filament reaches at around 1200 degrees Celsius. So during this temperature, iodine volatilized and combines with the impure metal to form metal iodide vapor, which decomposes on contact with the heated element to deposit pure metal crystals and liberate iodide for further reaction. So on metal deposition, the electrically heated wire increases gradually in thickness. In order to maintain the high temperature necessary for the decomposition, the current must be correspondingly increased. Because what will happen as soon as metal is going to get deposited in this electrically heated wire, so what will happen? The resistance of the wire will get increased with the coating of the metal deposition. So for creating the same impact or creating the similar temperature inside the furnace, we need to increase the current correspondingly as the metal is going to get deposited on the sample. Thus, the metal bar produced are limited in thickness. So, we have to optimize the thickness of this metal bars produced so that we don't have to increase more and more current during the operations. Coming to the next lecture. So, first we had talked about the physical refining processes. Chemical refining processes, which included refining by chemical transportation or distillation processes. Now we will talk about the physical refining processes. So refining by exploiting differences of physical properties between bulk metal and the impurities are used for two purposes. First one is the common example for physical refining process is refining of raw steel to create, or we can say secondary refining of raw steel to prepare specialized steel or specialized alloy or stainless steel. So having certain range of physical and mechanical properties. Then increasing the purity of certain metals or semiconductors used for the special purposes. So these types of refining processes generally include vacuum degassing process. So the use of vacuum degassing plays an important role in majority processes where vacuum is applied to remove dissolved gases inside the molten bath and or we can say volatile impurities from the molten bath. These processes are mainly applied to deoxidize the steel. So they are preferable to deoxidation by metals like aluminum, titanium, silicon because when added to steel, these are effective in reducing the oxygen content, but they form non-metallic inclusions. So some of which may become trapped in the steel during solidification and impair its mechanical properties. So instead of going for the refining with the help of these deoxidation metals, we generally go with the vacuum degassing process. So what will happen? We are trying to create the vacuum inside the ladle. So the oxygen entrapped inside the molten metal will come out and the molten bath will become oxygen free. So it is not going to create any inclusion inside the molten steel. that can create havoc during the further refining, during the further processing steps. Then there are other processes also like electric arc melting, zone refining, and distillation processes are other important physical methods which are generally used for the physical refining processes. So coming to the vacuum degassing processes during the primary steel making processes, gases generally entrapped inside dissolved gases which are oxygen, hydrogen, and nitrogen gases, which generally dissolve in the liquid steel, which have harmful effect. Uh, for example, loss of ductility or formability, because these gas are going to create the inclusions inside the uh, steel melt, and during the solidification, these gases will create the embrittlement effect during the solidification. And due to the formation of blistering, pinhole, porosity, numerous number of defects they are going to create during the solidification, and solubility of hydrogen and nitrogen in steel decreases drastically at low or room temperatures. So according to Sievert's law, the solubility of a gas in liquid metal is proportional to the square root of the partial pressure of that particular gas. So degassing as secondary steel making process is used mainly for the removal of dissolved hydrogen and nitrogen gases from liquid steel in molecular form. So small extent, while we generally we apart from these hydrogen and nitrogen gases, we can remove some small extent of oxygen and sulfur also during the vacuum refining process. So desorption of gases is a gas metal interfacial reaction. Thus, atomic hydrogen or nitrogen from the liquid steel must diffuse at the gas metal interface, where it is converted to molecular hydrogen or nitrogen gas like S2 and N2, which can then be desolved. The effectiveness of vacuum treatment less than 1 torr increases with increase in surface area of liquid exposed to vacuum. For example, in the form of a thin stream, fine droplets, or gas-induced stirring. So commercial vacuum degassing treatment of molten steel can be broadly classified into ladle degassing process, stream degassing, or circulation degassing processes. So these are different types of degassing processes which are generally used for the refining of the uh, steels in the plants, in the steel making plants. So these are the different types of furnaces. Then coming to the second process, like zone melting or zone refining process. So the method is based on influencing the segregation of impurities between a molten and a solid part of a metal. So the impurities being more soluble in the molten than in the solid phase. So that difference we are utilizing in the zone melting or refining processes for a liquid metal of initial composition C naught. So in this graph we can see two lines. One is solid line, another is liquidus line. So during the having the difference in the solubility in solid or liquid states, we can differentiate the pure molten metal and the impurities in the liquidus state and the solidus state. For a liquid metal of initial composition C naught, the first solid to form between of composition K C naught. The constant K is defined by the ratio of equilibrium concentration of solute in the solid and liquid. If K is less than unity, the liquid would be enriched in solute during solidification process. If a metal ingot is melted for a narrow portion of its length and this zone of fusion is moved along the ingot, pure metal will concentrate in the cooling portion while the impurities will be carried forward in the molten portion towards one end or the ingot in the direction of the zone movement. So due to the uh, solidus temperature difference between the impurity and the impurities and the pure metal which need to be refined, it will get moved further and further in the liquidus zone during the cooling process. So in the cooling zone we are going to get the pure metal, while in the liquid zone we are going to get the impurities will shift towards the liquidus zone, and in the end we can cut that impurity portion out after the proper solidification of the metal. So the main difference between zone melting and fractional crystallization is that one part of the charge is molten at a time in zone melting, where all the charge is molten during the fractional crystallization process. So this is a typical example of the zone melting or refining. So these types of processes are generally used for the refining of the gold metal for removing the impurities from the gold. Or in nowadays we are also using this zone refining or zone melting method for producing highly pure steel parts which can be used in the strategic purposes. These are distillation and rectification process. Okay. So now in the previous week lectures we had talked about the pyrometallurgical operations, uh, how to extract the crude metal via pyrometallurgical operations, and after crude metal how to refine them by using different processes, and what type of furnaces are required for pyrometallurgical operations, what type of refractory materials are required to build those particular furnaces, and what types of fluxes are required for creating the slag during those particular pyrometallurgical operations. Now there are some ores which can be which can be used for the extraction of metals in an economic manner via hydrometallurgical operations as compared to the pyrometallurgical operations. So now we will talk about the hydrometallurgical operations, what types of unit steps, leaching reagents, and methods are involved during these particular hydrometallurgical operations, like hydrometallurgy and their unit steps, various raw materials treated via hydrometallurgy, then comparison between hydrometallurgical and pyrometallurgy, like what are the advantages or disadvantages of hydrometallurgy or pyrometallurgical operations, then pre-treatment of raw materials required for hydrometallurgical operations, then common leaching reagents which are used in various hydrometallurgical operations, and or we can say hydrometallurgy of the various ores. Then types of leaching reactions involved during these hydrometallurgical operations, then practical leaching methods which are used in industrial applications for the production of different metals. So first we will talk about the hydrometallurgy and the unit steps involved in the hydrometallurgical operation. So hydrometallurgy is concerned with the production of metals, or we can say metallic compounds from ores or concentrates or intermediate products. We can say intermediate products can be considered as pre-treated ores, concentrates, or scrap or e-waste material, which is a buzz nowadays. So we are trying to recover, most of the metal manufacturers are trying to recover the metals from these particular e-waste. So they are going with a hydrometallurgical operation. So where metals are dissolved in aqueous solutions, or we can say these aqueous solutions can be having a different pH values and subsequently purified and recovered from aqueous solutions. So hydrometallurgy involves two different words. One is hydro, then second term is metallurgy. So hydro means water. So the aqueous metallurgical operations are known as the hydrometallurgical operations, which involves the uses of the acidic or acid, base, or salt solution to recover the metals from the ores or concentrates. So hydrometallurgical processes can be divided into five main unit steps. First one is pre-processing. So the ore or feedstock. So pre-processing is considered as the ore or feedstock or preparations which involve different beneficiation process or conversion process or different pre-treatment process to get them in the soluble forms. Then second unit steps is leaching steps. So this steps involves the dissolution of value metal bearing minerals or material fractions in any aqueous solvents, which can be acidic or basic in nature. Then third one is solid liquid separation. So after uh, leaching out, there will be some material which are not going to leach out in that particular solvents. Okay, so we have to go for the solid liquid separation. So we can extract out the desired liquid and undesired solid particles, or sometimes we are desiring solid particles and the undesired fractions will be the liquid. So solid liquid separation to get metal ion containing solution from unreacted solid residue. Then there will be solution purification. So purification and concentration of value metal containing solution. So sometimes what will happen? These aqueous solvents which we are going to use are not are not selective in nature. Okay, so many metals are going to get dissolved at the same times in those aqueous solvents. So from these aqueous solvents, we have to purify or reconcentrate our metals, which we are going to require for further operations. Then last one will be the precipitation, reduction or refining processes of refining of metals or compound in desired form and purities. So these are hydrometallurgy and their unit operations. Okay. So these are some various raw materials which are generally treated with the help of the hydrometallurgical operations like metals. If we talk about the metals, so precious metals like gold, silver, palladium, these are recovered with the help of the hydrometallurgical operations. Nuclear metals like uranium or thorium are considered for the hydrometallurgical operations because the quantity of these metals in their concentrate is on so much lower levels so that we cannot it will not be feasible to go for any pyrometallurgical operations to recover them. Like if we talk about the uranium concentrate, so uranium concentrate generally contains only 0.8 to 0.9% of uranium inside that uranium concentrate after which we are going to get after various beneficiation operations. While if we talk about the gold, so it will also going to contain around one or not more than 1 or 2% of gold. So we generally go with the hydrometallurgical operation for the refining of these types of metals. Then oxides and hydroxides like bauxite, laterites, uranium ores, zinc ores, and calcines. Then complex oxides like chromite or pyrochlorate or ilmenite. Then sulfides of the primary metals such as copper, nickel, lead, or zinc or molybdenite ore. Then phosphates, rock, monazite sand, beryl or spodumene ore. So there are different types of various raw materials which can be treated with the help of the hydrometallurgical operation. So if we talk about the comparison between hydrometallurgical and pyrometallurgical operation, so around 90% of metal ores can be treated either by hydrometallurgical operation or pyrometallurgical operation. Both can be treated by both hydrometallurgical or pyrometallurgical operation. But we have to decide the particular process in which we have to go based on the economy or the various factors involved during the processing of that particular ore. So, comparison between the pyrometallurgical, coming to the comparison between pyrometallurgical or hydrometallurgical operations. So, treatment of high grade ores is more economical in pyrometallurgical operations. While if we talk about hydrometallurgy, it will be less economical. While treatment of low grade ore will be more economical with the help of the hydrometallurgical operation as compared to the pyrometallurgy. While treatment of complex ore is also unsuitable with the help of the pyrometallurgical ore, while with the help of the hydrometallurgy, we can go for either selective leaching process, or if it is not possible to go for the selective acid dissolution, then we can go for selective precipitation or selective recovery process for that particular ore. While in the pyrometallurgical operation, it is quite difficult to treat those complex ores having 8 or 10 different elements because we have to separate them one by one. So that will include the number of steps during the pyrometallurgical operations. Then coming to the process economics, so pyrometallurgical operations are best suited for large scale operations requiring a large capital investment. While hydrometrical operation can be used for small scale operation, it has a lower capital investment sensitivity to plant size. Then treatment of secondary. So the major example for the process economics generally we generally go with the pyrometallurgical operations for the recovery of iron from the iron ore. While if we talk about copper, so it is more economical to extract the copper with the help of the hydrometallurgical operations if it is having very low quantity of material inside that particular copper ore. Then treatment of secondary resources, it is more suitable in the hydrometallurgical operations, while unsuitable in pyrometallurgical operation in most of the cases. Then separation of similar metals are not possible in pyrometallurgical, while it is possible in the hydrometallurgical operation. Then treatment of sulfide ore, sulfur dioxide is generated during the pyrometallurgical operations, while can be treated in hydrometallurgical operation without generating the sulfur dioxide. Then there are some pre-treatment in some cases. Some pre-treatments are required before going for the hydrometallurgical operation of the certain ores. Like some resources or ores in their untreated conditions do not dissolve by common reagents. Like generally industrially, most of the industries prefer H2SO4 as their uh, leaching material because it is cheaply available and easy to uh, deal with. Then pre-treatments, sometimes some pre-treatments are required to convert them so that they can be easily dissolved inside common reagents. So there are some examples of resources and what type of pyrometallurgical pre-treatments are required for their particular hydrometallurgical operation. So coming to the sphalerite ore, which is a ore of zinc. So, dead roasting is required to convert them into the zinc oxide so that it can be easily leached out during the sulfuric acid leaching process because it is difficult to leach out the zinc sulfide in the sulfuric acid leaching process. So, we need to go for the pyrometrical treatment of dead roasting process at around 900 degrees Celsius so we can convert them into the zinc oxide, and zinc oxide can be easily leached out in the sulfuric acid leaching process. Similarly, in the chalcopyrite leaching process, we can go for the sulfidizing roasting at around 680 degrees Celsius so that we can convert the copper iron sulfide into the copper, respective copper sulfates in the copper sulfate and iron oxide. So this copper sulfate is having very high uh, leaching efficiency in the water itself. So what will happen? With the help of the water leaching, we can extract out the copper sulfate, while iron oxide will remain as a residue. While coming to the pentalangite, which is a ore of nickel, so we generally go with the chloridization roasting process to convert the nickel sulfide into the nickel chloride, and that nickel chloride can be easily leached out with the help of the water only. Then coming to the laterite, which is also a ore of nickel, we generally go with a reduction roasting pre-treatment process so that we can convert the nickel oxide into particular nickel metal, and this nickel metal can be hydroprocessed with the help of the ammonia and ammonium carbonate leaching in the presence of the oxygen. Then coming to the zircon, which is a source of zirconium metal, we generally go with the alkali fusion at around 600 degrees Celsius temperature to get them converted into sodium zirconate that can be water leached easily and leaving behind the impurities. Then vanadium pentoxide is there, which we can go with the salt roasting pre-treatment process uh, for vanadium pentoxide to convert them into sodium sodium vanadium oxide that can be easily water leached. Then gold telluride is there, which requires some thermal treatment to convert them into the pure gold material, pure metallic gold, which can be easily leached down in the cyanide. While spodumene can be heated to about 1100 degrees Celsius and rapidly cooled down uh, so that we can leach that particular metal in hot concentrated sulfuric acid leaching process. While beryl can be melted and quenched and amorphous glassy product to produce an amorphous glassy product, which can be leached out in the dilute sulfuric acid leaching process. So coming to the leaching reagents, so leaching is the dissolution or we can say solid liquid mass transfer process of the valuable constituents of the ore in solutions from which metal can be extracted selectively. Leaching carried out at ambient conditions or at elevated temperature under different pressures. So leaching reagents, generally water is used to leach soluble sulfates or chlorides, many different chemicals or solvents Acid, bases, salts, aqueous, chlorine, etc. are called lixiviants, which help in metal dissolutions. So lixiviants should have the following qualifications. It must dissolve the ore minerals rapidly enough to make commercial extraction possible, and it should show chemical indifference towards gangue minerals. So it should be selective in nature, while it must be cheap and readily obtainable in large quantities. It should be regenerated subsequently after the leaching process, or we can say we can recycle back. Uh, it should be preferably non-toxic and non-corrosive to the plant equipment to minimize capital and maintenance cost of the leaching plants. Then coming to the leaching reagents, so there are some different classes of leaching reagents like acids, alkalis, salts, aqueous chlorines, and water, and different types of raw material which can be leached out with the help of these reagents. So, despite higher cost, basic reagents is economical to use as they are inert to acid consuming gangue like dolomite or limestone. Then, types of leaching dissolution reactions are some leaching dissolutions reactions are there. Then there are some leaching methods like in situ leaching process, dump leaching, high pressure autoclave leaching, heap leaching. Then so Then coming to the physiochemical aspects of leaching, the two fundamental parameters that is used to control the behavior of metals in aqueous solution are pH and the oxidation potential. Uh, One is pH and another one is EH of the solution. So these two parameters are required to create a particular environment for the proper leaching of the desired metal, or we can say with the help of these parameters we can vary the selectivity of the acid lixiviant for the particular metals or ores. The thermodynamic behavior of an aqueous system is determined by these two parameters together with the concentrations or activities of dissolved species. The oxidation potential in an aqueous system primarily determines the valencies or oxidation states of metals and ligand species, and this in turn governs whether or not the species are soluble or not soluble. All metals and alloys and most metal sulfide must be oxidized by adding oxidizing agent in order to become soluble. Like ZNS is not going to get dissolved inside the acid solvents, so we have to convert them into the into the respective metal oxides, or we can increase the oxidative potential of the solution with the help of the oxidizing agents, or so that we can increase the oxidative potential so that that can be easily leached out inside the solutions. With higher valency metal oxides, leaching under reducing conditions may be necessary, like manganese dioxide having +4 metal, +4 oxidation state is not viable for the leaching operations. So what we have to do, we have to reduce the +4 oxidation state of the manganese dioxide to the +2 oxidation state of the +2 oxidation state, so that it can be easily leached out inside that particular leach solution. So an adaptation of considerable utility in hydrometallurgy is the oxidation potential EH versus solution pH diagram, which is also known as the Porvex diagram. Constructed from aqueous thermodynamics data, it can be of great value in selecting the solution conditions necessary not only for dissolution of solid species but equally for the precipitation of solid phases from processed liquors. So these are the oxidizing agents in increasing order of oxidizing potential, which are generally used in during the oxidative or reductive leaching processes, like Fe3 plus having a potential of 0.77, while ozone is having an oxidation potential of around 2.07. Uh, Generally, the oxidizing agent which are generally used in the during the leaching processes are HNO3 or H2O2, or sometimes we use KMNO4. Ozone is generally not generally used for the not generally used as an oxidizing agent due to the high cost of the ozone gas. However, in some cases, we can use the ozone gas as an oxidizing agent during the acid leaching process to increase the oxidative potential of the acid leach solution. So this is the four types of Corbett's diagram which we can create. Then now coming to the bacterial leaching techniques have grown into a technology that is now known as biohydrometallurgy. So bacterial activity can be direct and indirect leaching of metal sulfides. In the direct leaching process, the sulfide minerals are oxidized to metal sulfate. So in the biohydrometallurgy, or we can say bacterial leaching process, what we are going to do, we are going to provide some bacteria. So these bacteria under oxidative conditions are going to convert these uh, metal sulfides, or we can say metal. Sometimes in most of the cases, these types of leaching processes are applied for the metal sulfides only, so that we don't need to get them converted into metal oxides via dead roasting operations and further process them with the help of the acid leaching processes. So generally we go with the biohydrometallurgical process. With the help of the bacterial activity in the presence of the oxygen, what the bacteria will do, it is going to get them converted into the respective metal sulfate. So in case of MS plus 2O2, bacteria is going to get them converted into MSO4 by oxidation. While if we talk about the Fe sulfide, so with the help of the bacteria, it is going to get converted into Fe sulfate, and at the same time, it is going to produce the H2SO4 acid in the liquid condition. Both FeSO4 का whole iron sulfates and hydrogen sulfate participates in the indirect leaching processes, as Fe3 plus is an important oxidizing agent which can oxidize sulfides to sulfates. The role of bacteria in the indirect leaching mechanism is to deoxidize Fe2 plus to Fe3 plus and elemental sulfur to H2SO4, and this H2SO4 is uh, going to take participate in the leaching process of the uh, other metals. So generally, this bacterial leaching processes nowadays in at industrial level they are using for the leaching operation of CuFeH2 chalcopyrite ore for the leaching for the selective leaching of copper from the very low grade chalcopyrite ore. So what they are doing, they are going with the heap leaching process at the mine site itself with the help of the bacterial leaching, so that they can leach out the copper in the solutions with the help of these bacteria at very low cost. So different types of bacteria which they are using in the bacterial leaching processes are thiobacillus thioxidans, thiobacillus ferrooxidans, ferrooxidans, and ferrobacillus sulfooxidans. So these are different types of bacteria which they are using for the bioleaching processes. And apart from the copper extraction process, they are also going with for the uranium extraction, which can be expressed by the indirect mode of bacterial action in which Fe3 plus oxidize the insoluble tetravalent uranium to its hexavalent state that is soluble in the acidic leach media. So with the help of bacteria, what